Alrighty guys, we're going to go ahead and get started with one of these Coulomb's law problems. This is probably the most difficult one that we do for the beginning half of electrostatics, and this one has to deal with levitation. So let's go ahead and read through it. A person who has a mass of 70 kilograms is standing on top of a platform in the front of the classroom. This platform is about 0.45 meters off the ground, so I can write that, 0.45 meters. Imagine they had 2.5 times 10 to the 15 extra electrons on the bottom of their shoes. Also imagine that there were enough extra electrons on the ground below them so that when they stepped off the platform, they levitated at that distance of 0.45 meters. So here's our picture over here to the right showing that, right? I see them, they're levitating. The distance from here to here is that 0.45 meters. Awesome. While levitating, the downward force on the person is what? So basically what this is asking is that as this person levitates, what is pulling them down? So in other words, we have to draw a free body diagram. What force does the person feel pulling them down towards the center of the earth? Well, that's always force gravity. So over here, I can answer force gravity. What is the upward force? Well, why are they levitating? They're levitating because there's electrons on their shoes and electrons on the ground, meaning that there is an electrostatic force pointed upward. So I can put that over here. Next, these forces are blank. Well, again, keyword, levitating. And because they're levitating, that means that they're not moving. If they're not moving, that reminds us that net force is equal to ma. If we take the forces that point up, in this case, electrostatic, minus the force that point down, and set that equal to ma, we can figure this out. We know that because they're levitating, they're not moving, so this is just 0. Meaning that the electrostatic force is equal to force gravity. Therefore, these forces are balanced. All right, now that we figured out the conceptual stuff, we can go ahead and dive into the numbers. What is the charge of the electrons on the person already? So initially, it tells us that that person has 2.5 e to the 15th electrons on them. We know, though, if we look at our equations up here, we have Coulomb's law, charge of an electron, and mass of the electron. If we are trying to figure out the charge on this person already, we need some sort of equation or conversion from electrons to charge. Fortunately for us, that's right here. Therefore, if I set up a ratio really quickly, given the fact that I have my electrons here, I know that actually negative, because they're electrons, negative 1.6 e to the negative 19 coulombs is equivalent to 1 electron. Now I notice that I have electrons on top here, electrons on top over there. All I have to do is multiply through to figure out my charge. Doing so, I get a charge of negative 4 e to the negative 4th coulombs. Next question says, calculate the charge that would be needed in order for this person to float. Well, before we do that, let's go ahead and list all of the information that we have. We know the mass of the person, and the mass of this person, it said in our problem, is 70 kilograms. We also know the distance, and that distance is 0.45 meters. Another thing that we know, which we just figured out, is the charge on that person's shoes. So Q1, and that is negative 4 e to the negative 4th coulombs. Lastly, we know what K is, because K is a constant, that's 9E9. And then we also know, and we'll explain it in a sec, what the force is here. How do we know what the force is? Well, we know that that force is equal to the force of gravity. So electrostatic force equals force gravity. And if we remember, force gravity is really just mass times gravity, which is just 70 times 9.8. So if we multiply those two together, we get 686 newtons. Go ahead and plug that in over here. So now let's go back to this question. It says calculate the charge that would be needed to add to the ground to make us float. Therefore, we need to figure out what Q is. So if we have our equation, force is equal to K, Q1, Q2, all over R squared. That means that I'm solving for this value here, Q2. Well, instead of me plugging in my numbers and then solving, I'm going to manipulate my equation first and then solve. So in order for me to do that, I'm going to multiply r over to the other side, r squared over here. So that's going to give me force times r squared is equal to K times Q1 times Q2. Next, like I said, we need to get Q by itself. So I'm going to divide both sides by K and Q1. K and Q1 cancel out over here, and I'm just left with the equation I need. Q2 is equal to force times the distance squared divided by K times Q1. Let's go ahead and plug all of our numbers in here and solve. Q2 should be equal to our force, which is 686, times R. R is 0.45, square R, and then divided by K, which is 9E9, times our Q1, which is -4, e to the -4th. I'm going to go ahead and add parentheses around all this stuff so I don't get confused, and some brackets. Once you solve for that, you should figure out that Q2 is equal to -3.86 e to the -5th coulombs. Last thing we want to figure out is the number of electrons that we need to add to the ground now. Well, this is actually kind of working backwards from our first problem. So we have -3.86 e to the -5th coulombs of electrons, and we know that one electron has a charge of -1.6 e to the -19th coulombs. Coulombs on top here, coulombs on the bottom there, those cancel out. All I do is multiply through, and I find out that I need 2.41 e to the 14th electrons in order to make this person float.